But then we had to run a process where in all these competitions you have given a learned data set. But then you're asked to run the predictions on a new data set for which the target is not known. Whenever we have that situation, very early into the process, we run the test that compares both data sets. And the way it runs is roughly like that. You take the learned sample, you introduce artificial target, set it to 0 on all records. Then you concatenate that data set with the test sample. And that artificial target is now set to 1. So you have a combined data set, but you also know the source where the record comes from. Then you want to run a tree, and what you really want to see is the worse the better situation. You don't want to see any model. It's one of those unique situations where not having a good model is what you're looking for. Because what it means, no matter what you do, you cannot separate which part of the data the record comes from. In that competition, it was the case. We got a tree that looked like that, and we got a relative error that looked like that. Now, normally, you'd be pretty upset if you saw relative errors like that, unless you work in the stock market. But in this case, it was a very good sign for us, because it kind of unleashes your hands. Now you know you are given a learned sample that comes from the same population as the test sample. Only happens in competitions and not each and every one competition. In real life, you will have situations where you have to learn on one part, and then you have to apply on another part, either at a different point in time or at a different point in space. Unfortunately, of course, it has all kinds of philosophical connotations because you're kind of betting on luck. You're assuming that whatever you learn today, even as the time goes on, things are likely to change. Nothing is static. But you're kind of betting on the fact that even if things drift, they're not going to drift drastically away from what you currently have. But no statistic in the world, no magic algorithm in the world is going to help you deal with the dilemma of changing model and all the time drift. And of course, the stochastic processes it's probably the fanciest, the most complicated subject that you'll find in statistics, even though they can only handle pretty trivial situations that you're unlikely to see in your data. So we're kind of betting on luck, but this is a very good experiment. And regardless whether it's competition or not, you can always investigate what happens to your population as things change. Now, we had one situation when they built a model for a major insurer, and they were quite happy with that model, how it performed over 6 months. And at some point, they came back to us and said, something is wrong. We can't figure it out, but all of a sudden, model predictions are collapsing. I mean, we are no longer observing what the model is predicting. So what do we do in this case? Well, we say, give us your new data. So we have original data that was used to build the model. We have the new data. We run that concatenation operation, run it through CART. Whoever emerges on top is the variable that is responsible for the key difference between the two parts. Now, what you will discover is that initially it could be a trivial variable, say something that's related to date. Of course, that's not very interesting, so you kind of pull it out. You exclude it. Then you do that so-called shaving from the top process, and at some point you kind of weed out interesting sources of variation. Now, why is that also important? You may discover that when you build a model now, by the sheer nature of learning process, some variables have advantage over others. So the learning algorithm latches onto those variables and uses them because that's ultimately what works best in the current data set. But suppose those are the variables that are likely to change in the future data or changed recently. Well, operation like that would allow you to identify those variables, and you could conceptually pull them out and rebuild your model looking at the set of variables that's more stable over time. You may lose accuracy on the part of the data that you had before, but you will make it more stable in the long run because you're now focusing on the part of the data that is not changing chaotically. But anyways, going back to that insurance company, we ran that experiment, and immediately the variable that emerged on top was the variable related to region. It turns out that that insurer decided that it used to be located only on the East Coast, and they've decided to expand their business to cover the West Coast. And that variable immediately emerged, and guess what? It was a categorical variable related to area. It was a very powerful predictor in the original model, but it was useless for all of the records in the new customers because they were coming from the kind of gray, shadowy area. I mean, it's trivial, but it was very easy to find it running these experiments. So never forget that concatenation trick. It emerges in striking different situations, and it's always good and it's always insightful. You can include any variables you like. Usually include them all, and then you start eliminating trivialities. So you're kind of saying, oh, okay, yeah, that of course makes sense. That variable would tell the difference. So let's exclude it from the keep list, run it again, and you sort of gradually, very quickly gaining some knowledge on what accounts for the differences. The challenge number 5, that's the big one, the dimensionality reduction. And what we have here is a number of automation battery techniques. This is basically one of the most powerful batteries that we have currently in cars, aside from battery target. And we call it variable shaving. And it's a very trivial thing. I mean, all the classical regression techniques are doing something like that. You start with a full list of predictors. You build a model. Then you look at the variable importance, and you systematically proceed by eliminating, well, usually first thing that comes to mind, eliminating least important variables. But what we recommend is that you have to start by eliminating most important variables. Why? Precisely because of that model hijack situation that we've experienced time and again. So what happens is you have a learned sample and you have a test sample. It's a learned sample from one point in time, test sample from the next period in time. When you build a model, let's say TreeNet. TreeNet has no access to future data as the model is being built. It only uses it to validate the performance and suggest optimal number of trees. What may happen is that the TreeNet will be fooled by tracking the variable that's extremely powerful in the learned sample, but it changes in the future data. So you'll get that variable as on top of the importance list, but the test performance may collapse. You'll have an overfitting gap, as we call it. You look at the performance, and you see your learned performance improves dramatically, but your test performance lags behind, creating that ever-increasing gap. First thing you do, you remove the most important variable and see if it actually improves things. You will be surprised how many times it does. In particular, when you deal with high-level categorical variables, you remove the variables that are overly aggressive on the learning stage. The TreeNet will have no choice but to pick other variables, and those might become turned out to be a lot more stable and more useful with respect to the test sample. So you do it with the top variable, you do it with the next to the top variable, you do it with every variable, say within the top 5. So you want to be absolutely sure that removing any of those top 5 variables one at a time causes a significant drop in model performance. And it's only after that is being achieved, then you focus at the bottom of the list and start weeding out all of the least important variables one at a time, until you produce some kind of performance summary like that. Here I'm showing area under ROC curve on a sample run that started with 37 predictors in the TreeNet fashion. And as the variables are being eliminated, you have this chaotic pattern at first, but then it substantially drops in terms of area under ROC curve. And if model simplicity is one of your concerns, that this is the good kind of scree point